Hello, today I want to implement the Kruskal algorithm in Haskell. I assume that you already know how it works, but I talk a little bit about how it works. Okay, at first the Kruskal algorithm take on input some graph and produce on output some minimum spanning tree. Okay, it takes this graph, takes a list of edges of this graph and sort this list in ascending order. When they pick up the first edge, and they can construct the first connected component. So when they pick up the next edge, the second edge, we can check. Here we go to some cases. We can check if this edge is connected with the first edge or not. If it's connected, what I mean connected, that I take the two vertices of the second edge, V1 and V2, and we check if these V1 and V2 are also presented in the first stage. If some of them are presented, then this means that they connected and they in the same connected component, and they somehow merged these edges to one connected component. And so on, the extract the edges from our list and stop. Then our list is empty. Also, these keep edges if they in the same connected component, because this leads us to cycle, and our spanning tree should not have cycles. Okay, let's start to implement. So we'll start with as always from type signature. I will name my function Kruskal, and it takes some graph of type A, of vertices of type A, and length of the edges L. And on output they produce a list of edge type. So here they have this type. And here all our graph representation. If you know a little bit about graphs, please see my first intro to graphs in Haskell. In that video I explained all the step by step of what all these functions. Okay. On output we need to produce a list of edges. And let's go to implement. We take some graph and we will use some helper function. I will call it go. This function at first it will take some params. At first it will take some integer, I will call it last index. This integer represent the marker to the connected component, to the current connected component. So I will explain it a little bit later. Then we have some mapping. This mapping from vertices to the integers. And these mappings show us which vertices belongs to some connected component, to which connected component. And the next parameter is edge list. This is our sorted list of edges in the ascending order. And the last parameter is our found edges, which from which our minimum spanning tree consists. On every iteration we will increase this list by 1 by adding the age. Okay, so actually we extract some age from our sorted list and put it to our final result if the vertices of this age not in the same connected component. So if they not build a cycle in our result. Okay. Now we can define some of these values. For example, I can start to mark my connected components as 0. Next thing, I need to define mapping, which is empty at first, and this mapping maps our vertices to connected components. So it has for case it has type as vertices of the graph, and for values it has type int, which represent the somehow identification of the connected component. Next thing we need to define is our edge list, and we can define it by sort by function, which sorts our list of edges, and our list of edges we can extract here from our graph. We can pattern match it, and our graph we know that our graph here is represented as the list of edges. Okay, and we use this here to pattern match it. Sort by function. Let's look at its type signature. Sort by. I think I need to import data list. And you can see that this function takes some function as the first argument, which takes two values of our list and produce the ordering type. This means that so I will skip it for a moment, but now I know that I need this list of our graph, and here I can use some lambda function which can pattern match 2 of our age and return something. So how we can pattern match our ages? We pattern match them like this. We have such a data constructor, and we pattern match every of the age like this. But here we have some vertices, and no matter what these vertices, because we want to sort only by the length. So, and I can proxy this comparison to the comparing of the lengths. Okay, and this will give me the sorting our list by length of the edges. Okay, next thing we need to initialize our found list, in which contains the edges which are accepted in our spanning tree. And now I think from here we can go to definition of our go function, of our iteration function, and we push all the parameters which we already initialized. So here we push them, here we define our function. Okay. Our iteration process stop when all our edges, when we extract all our edges from our sorted list, and we can check it like this, and in this way we return our found list. Otherwise we go to recursion, we run our function again with some new nodes marker to mark the new nodes of the to the new connected components. So we increase the each by one iteratively if we use some of previous marker. Okay, and of course we need to update our mappings with which shows the connection between vertices and connected components, and also we need to provide new list and new found edges. Okay, here we need to go to definition of our new parameters on the next iteration of the iteration process. So at first we can input or match our edges list. We can extract the first edge and the tail of the list, which they can use to proceed our iteration process. And here we will have an edge, and this means that we can input or match this edge like this, but I want to know the vertices of the minimum edge, and I want to have its name at all. And of course I want to know its length, I think like this. And now I need to define a new mapping. So I somehow, in this step, I somehow built a connection components. And now I have some cases here. The first case is then the both of the vertices are not in connected component. So at first, at our first step, we have no connection components at all. We pick out the first edge and we want to build the first connection component. And I will check this case with some boolean value. I will give name to it is both of our vertices not in connection component. And in this way we need to create a first connection component. And how are we doing this? We use an insert function of our map. We put at the first vertex the first vertex we connect with our last index of the connected component. And of course we use our initial map. Okay, and we will receive a new map, and of course I need to, because both of our vertices not in our map, I need to add both of them with same last index. and after that I need to increase this index, of course. But I will define it increasing later. Okay, I do this, and we go to some next case. What if our first and second vertex is in the same component? So here I write just names. I not defined how to evaluate them. I will define it later. Now I use only logic to define these things. So if they in the same component, this means that I need to stay my mapping as it is, and I need to skip this h at all. So I defined the new mapping as the old one. Okay, now we go from here to cases. What if only vertex 2 in component, in some component, and vertex 1 not in some component? This means that they need to add the vertex what is not in component to the component of vertex v2, and this is easy to do. We can insert the vertex 1 without the component. We can add to it component of vertex 2. I will define it later, but we modify our map like this. And we have another case if only v1, some symmetric case if only v1 in component. Otherwise, of course, the insert to the 2 in which is not in component, the component of v1. And we go to the last case if all the vertices is both in different components, is both in different components. This means that they need to merge them somehow, and I also will define this thing later, but now I just mark that I need to merge these two components. Okay, we do the definition. Now, before I go to merging, I want to define all these Boolean values. But at first I want to define how we calculating our how we extracting our components for our vertices. So we can easily define this thing, these components like this. They can use a map, and where exists one interesting function which has name find with default. So it's tried to find some key in the map, and if this key is not presented, then it returns the default value. And as default value I will use -1, and I will if I want to know the component 1 for vertex v1, I need to provide the 1 here and our mapping. And I can say that this thing has the type int. Okay, and also for v2 I need to find v2, and it also has type int. Okay, now let's define this thing. So how to define the Boolean value which tell us if is both not in component. This means that the both case of CV1 and CV2 have -1 value. So this means that CV1 equal to CV2, and also CV1 is equal to -1. All of them equal -1. This is mean that they now have the component, and they need to provide here by two insertion the component to both of them. Okay. What if we have same component? How can they define that the two components are the same? This means that we need to check that components are equal, and that the sum of these components is not equal to -1. This means that both of them not equals to -1, and this means that they both are in some component. Okay, from here they can go to define this thing. It can be defined as so if only v2 in component, this means that CV2 not equal -1. Okay, this means that it in component, and CV1 is equal to -1. Okay. In that case, they can say that only v2 in component. Okay. And also otherwise, if they have v1, we CV1 not equal to -1 and CV2 equal -1. Okay, I think like this. And the last definition, if they both in the different components, how can they check this? We can check this if CV1 not equal to CV2. Okay, and also we need to check that CV1 not equal to -1, and CV2 not equal to -1. I think like this. I hope I don't do any errors. Yes, I think this thing should work. Now I can define my new last indices of the integer which marks the connected component. So we increase only if we do some do some marking on the one step of the new marking if the both of the vertices is not in the same component. So this means that I defined it like I use if they not both in the same component, that this means that they use our marker here, and they need to increase it. And I increase our marker. We defined it as plus 1, I think. And otherwise this defined it like it is, so we don't touch it, skip, it stay the same. Okay, and now let's define our result, how our result changed during our iteration. Our result stayed the same only in one case, if we have if the vertices in the same component. This means that they have cycle here and we need to stay it as it is, and otherwise we need to add our edge to our find result. Okay, I think something like this should work. Like this. Okay. Now I can, at the end, I can go to the definition of our merge function, and how we will define merge. So when they merge in two components which represented as our mapping. So let's first define the structure of our go, not structure, the type signature of our go function. It take int as the first argument. This is a marker. When it take the mapping from vertices to connection component in identifiers, and also it take a list of edges. I can get it from here, and then it takes another list of edges with the results, and here they have the final result. Okay. Now I go to the merging. How we merge? They take two vertices. Each of them have the different components in our mapping. We extract the maximum component, and all vertices what in the minimum component, all these two components, we change it to the maximum component. So this is exactly our merging process. And how can we do this? Actually, this merging is here we doing it's via updation of our mapping, and this updating can be done in some arbitrary number of steps. So it's somehow insert, which do the updation, and we can use the fold function for this. Okay, I will put its type signature here. Fold L function, and I will provide some function, insertion function. Also I need to provide initial mapping, of course it's our received mapping, and then I provide a list of case to updatable case of the minimum component. And here I need to do definition. I need to define my ins function, which takes some mapping, some k, and it's do inserting. It's do inserting this k to this k. This is some this k represent the minimal the vertices of the minimal component, and they update them with this insert function with the max component, and they use this mapping m that you received on input. So, and now I need to of course define my max component. I can define it easily by selecting the maximum from component v1 and component v2, and also I can define the min component. I also need this component because I will use it to find all the vertices which have this component. So I will find them from our initial map. If I know the component, I can extract all the keys which have this component. So our map have the mapping from keys to values. If I know the value component, the value which represent the component, I can find all the keys, a list of keys. And this means that I need to update case, and here I will use some function. I just don't want to talk how it works. It just take the mapping, it take its value and find all the keys which maps to this value. It can be a list of keys. So we defined our keys. This function let's copy it from here. Look up case, and we provide as well our minimum component and our mapping. Okay. And I think that's all. This should work. Let's try to load this file. Load go. Okay, we have some errors. Okay. Here I need to use equality, not equality. How this sign? No matter. So we need to use this sign here. Variable not in scope. Okay, I think I make some type error. She's 16. So I think I need to split this thing. CV is same component. CV equal to CV2 and one of them, for example CV1 not equal to -1. Here variable not in scope A. Data constructor not in scope A. Of course I do the type error here. Here I want to say that we have the map of A and int, like this, I think. So next I think I need to add orderings, some orderings in the type signature, and also for all AL, and some constraints some constraints. I need to have ord A, ord L, and that's all, I think. Yes, it's done. And let's try to use this graph to find the minimum spanning tree. So we have this graph, and I reload my module, have this graph, and I run Kruskal G. And you can see that I receive the all the vertices, all the minimum span, all the h of the minimum spanning tree. Here we have this maximum h of 3. It was skipped, and I think it's worked as it is. So this was a implementation of the Dijkstra algorithm. Of course, it used somehow this mapping which represent the mapping from vertices to components, but more efficient to use a disjoint union data structure. In this way, it can be it can be done more quick merging. This merge function, actually this function not very effective because it's not use this disjoint set data structure. But in this video I just want to focus on the Kruskal algorithm, and maybe in the next videos I will implement the disjoint union and will improve this algorithm with this data structure. So guys, thanks for watching. Push like, push subscribe button. It motivates me to do more, and if you find any errors, I don't do any testing, please write comments. I will fix them, and you can find this code in the description. I will put it in the gist. So see you in the next video. Bye bye.